So when you start getting a lot of ratios that are equivalent to each other, right? 1/4 is equivalent to 2/8, which is equivalent on and on and on infinitely in both directions, might I say. It can just be a lot to manage, right? There can be a lot of data that can get a little confusing if you don't have a way to structure it or organize it. So you can use a tool called a ratio table that can just sort of keep your data nice and tidy for you. So in this case, you'll see here that equivalent ratios can be organized in a ratio table. We have, so give two equivalent ratios in the table. So we have some data in the top or the numerator portion of our fraction. If you think of this like a fraction bar, we have boys, and in the bottom we have, or the denominator spot, we have girls. So if we want to create some equivalent ratios, we can do the same thing. We can scale up, we can scale down, right? We can multiply, we can divide. So let's start by scaling down. I always find it handy to have a 1 inside of your ratio because it becomes easy to then kind of multiply it or divide it by other things. So let's say, well, what can we do to this 2 to turn it into a 1? Well, we can divide it by 2. So if we do that, then we get a 1 boy for every how many girls? Well, we need to divide the girls also by 2 to keep the ratio equivalent. Well, 5 divided by 2 gets us a number that's not whole, and that's okay. So we could have a 2.5 to 1. So 2.5 girls for every 1 boy, sort of in the ratio world. Doesn't mean we're like splitting them in half, but just as a ratio. So we could also scale up. So you could say, well, let's just multiply, I don't know, each by 2. So if we start with 2 boys and we double the amount of boys in that space, then we have 4. And if we double the amount of girls, because we have to do the same thing to both parts of our ratio, then we end up with 10. So we have a 2 to 5 ratio is the same as a 1 to 2.5 ratio, which is the same as a 4 to 10 ratio, all equivalent. So now down here, we're going to do the same thing. So we're going to complete each table with 2 equivalent ratios. Okay, so we're given some info. We've got some blueberries, we've got some strawberries. And in this case, we know that there are 8 blueberries for every 3 strawberries, right? So we could think of this as a fraction bar. We could give it like a colon, whatever works for you. So we can scale up, we can scale down. So let's just start by scaling up. Let's just double them. So if we double 8, we get 16. If we double 3, we get 6. So a 16 to 6 ratio is the same as an 8 to 3 ratio. It just looks different. You could also scale down. So we could divide, we could either work with the 8 to 3 or we could work with the 16 to 6. So if we divide 16 and we divide 6, well, we don't want to divide them by 2 because that'll just get us our original ratio, right? So we could divide each by something else. We could divide it, say, by 4. We're going to end up with a number that isn't whole, but that's okay. So when you divide 16 by 4, you just get 4. And when you divide 6 by 4, and you're welcome to use a calculator in this realm because we're not explicitly practicing the skill of division right now. We're just applying it. So when you divide, you get 6 divided by 4 is 1.5, which makes sense that there's going to be one whole, or at least a whole, because this is an improper fraction or ratio. So a 4 to 1.5 ratio is the same as a 16 to 6 ratio, which is the same as an 8 to 3 ratio. You could do as many of these as you want. You could do these your whole life, right? There are infinite equivalent